Thank you very much for the introduction. And first of all, I'd like to thank to the organizers for inviting me. Actually, I was first asked to invite the invitation from Rukmini. Was 5 years ago, and I accepted, and I even bought that flight ticket, but then because of the COVID, the workshop was canceled. So, so I'm very glad to finally come to here. So, and I'm from Hiroshima, Japan. So this is not the university, but it is atomic bomb dome. It's located in the center of Hiroshima. And so this is kind of famous place for tourists, Hiroshima city. And also we have another famous place for tourists. This is called Miyajima. It's the island and the big shrine. And this is the gate of the shrine, but the unique point is the shrine is in the ocean. So this is also a very famous place. And this island, there are many, many deers walking around the road. So if you have chance to come to Hiroshima, please visit. And this is my university, Hiroshima University. And this is not in the center of Hiroshima, but the city next to Hiroshima. So it is surrounded by many, many trees like this here in ICTS. So yeah, please come to my university if you have a chance. Okay, so let's start mathematics. In these lectures, I will give a talk about zero mean curvature surfaces in Lorentz Minkowski space. But today, I will focus on the maximal surfaces in Lorentz Minkowski space. And the first half, I will give some brief introduction of these surfaces. And then the second half, I will show an example of explicit construction of maximal surfaces with positive genus. Okay. Now, let's start. Later I will restrict my talk to L3, surface in L3, but first, for a while, I will give a talk for hypersurfaces. We denote Ln+1 is n+1 dimensional Lorentz Minkowski space. This is the same as a set of, this is the same as Euclidean space as a set, but the inner product is different. So we have this inner product. So we have minus here. Okay, and so the vector v in Ln+1, which is non-zero vector, it is called space-like if is space-like if inner product of V VV is positive, and it is time-like if and only if VV is negative and V is right-like. Then VV equal to 0. Okay. And also we say V is future pointing if the n+1, n plus first component is positive, then V is past pointing if the n plus first component is negative. Okay. And let U be a compact set in Rn, and we denote the coordinate here. And so the immersion f from U to Ln plus 1 is space-like if the induced metric is positive definite. Okay. So this means any tangent vector is a space-like vector. So then in this case, we say the immersion is space-like. Okay. And we denote by Hn plus minus the hyperbolic plane, hyperbolic space of n dimension. So this is x1, xn, and this direction is xn plus 1. Then we have right cone here, and Hn plus is the upper half of hyperboloid. Hn plus, and Hn minus is here. Okay. Okay. Then if f is a space-like immersion, then we can take the unit normal vector field along f, nu. So nu has the property that nu is pointing at Hn plus or Hn minus, and such that the inner product of nu and any tangent vector of the surface is always equal to 0. And also nu is time-like and the unit. So inner product of nu and nu is minus 1. Okay. So we can take this unit normal vector field nu for any space-like hypersurface. Okay. Then in this, with this unit normal vector field, we can define the second fundamental form. And also, f is immersion, so we can have first fundamental form. And then using first fundamental form and second fundamental form, we can define the shape operator and taking a trace and divide by n. Then we can define the mean curvature of f. Okay? And we denote this mean curvature by h. Okay? And let f be a space-like immersion, and f sub t a variation of t. So this is a boundary fixed variation. Okay. And we denote by nu the unit normal vector field on f along f, the original f. So not the variation. Okay. And h, the mean curvature of f. Okay. And dv, the volume element. Okay. Then we have the first variation formula of the volume of f. So this is volume of ft. We divide it by, we take a first derivative by t, then get t equal to 0. Then we have this equation. So we have beta is here, defined here, and so beta times h dv. Okay, so the computation is almost the same as Euclidean case. And using this variation formula, we can say this. So this first variation is equal to 0 for any variation of f, if and only if this is the mean curvature. The mean curvature of the original surface is identically 0. So, so this direction is obvious because this h equals 0, then this is always 0. But the other direction is not really trivial. But if h equals not vanishing identically, then there is a suitable variation so that this integrand is positive. So this doesn't. So there exists a variation so that this volume becomes maybe negative. So so this holds. Okay. And then also, so at least if the mean curvature of f vanishes identically, then the first derivative is equal to 0 at t equals 0. So it can be maximal, volume maximized, or volume minimized, or some stationary point. But then, yeah, in this situation, we can compute further derivative, the second derivative of ft. Then we have this equation. So yeah, so beta is again here. And Laplacian G is Laplacian with respect to the first fundamental form. And this A is second fundamental form. So this is a norm of second fundamental form. And this is also gradient with respect to G. So we have this formula. This is quite, we need long computations, but yeah, straightforward computation, but extremely long. Okay, so then using this second variation, we can see the, not yet. We can see the stability of, we can consider the stability of the hypersurface. So suppose that the first variation vanishes for any variation. So this means h vanishes identically. And in this setting, f is stable if the second variation of f is always positive, or always negative for any non-trivial variation. Okay. So, and in this case, in our setting, the inner product of nu and nu is always negative because this is time-like vector. And yeah, we take the unit normal field, vector field as for a future pointing. So n plus first component of nu does not change. The sign does not change. We have the following. Let f be a space-like immersion with vanishing mean curvature. Then the second variation of the volume is always negative. So that is, f is stable and has maximal volume. Okay. So this is pretty different from the minimal surface in Euclidean space. In the minimal surface case in Euclidean space, the sign of second variation depends on depends on u. So if u is very small, the second variation is positive, but nu getting bigger, then the second variation might be negative for some variation. But in maximal surface case, this is always negative. So this means first variation is 0 and second variation is negative. So this means the volume of surface with vanishing mean curvature is maximal. So we call this the surface space-like immersion with h equal to 0 is called maximal hypersurface. So not the minimal surface, but maximal surface. Okay. So now let's consider the graph hypersurfaces. Let U a domain in Rn and point U denote by this. And also phi, let phi be a function on U. Then we have the graph. And the mean curvature of the space-like graph of hypersurface satisfies this. Okay. So this is just gradient like vector analysis. And in Euclidean space case, here we have plus here, but in this case here minus, we have minus here. And this means graph is space-like. So this corresponding to the, this is equivalent to the graph is space-like. Okay. So then if phi satisfies this equation, then the graph is maximal hypersurface. Okay. And vice versa. So this equation is called the maximal hypersurface equation. Okay. And when the n equal 2 case, we set u1, u2 equal to xy. Then this above equation, this equation is equivalent to this equation. Okay, so this is this. And this can be computed as this. Okay. So this equation is called the maximal surface equation. And the minimal surface equation, we have plus here and minus here, plus here. Okay, so signs are a bit different, but the similar equation we have. Okay. So, but we need to this inequality for the surface to be space-like. So this is a kind of big restriction. Okay. So by using this equation, Rabi said the graph maximal surface defined on entire R2 must be a plane. Okay. So this is the same as minimal surface case. Graph minimal surface defined on entire R2 must be a plane. This is called Bernstein's theorem. We have the same theorem. But we can say somehow more stronger result. But so, yeah. So we have this equation with this inequality. So this corresponds to the surface to be space-like. So this is very quite strong restriction. So if we don't assume this, then there exists a nonlinear example. For example, so there are many examples, but one easy example is phi equal to log of cos x minus log of cos y. So this is entire function, but some part this is negative, and some part this is smaller than 1, and sometimes some part this is greater than 1. Of course, there's some part that equal to 1. So in a minimal surface case, we have similar equation, but here just cosine. So the phi is not defined entire R2. And this is, the surface is called Shark's surface. So this inequality is pretty strong. And also, this is a theorem by Calabi and Chen Yao. The graph maximal hypersurface defines an entire Rn must be hyperplane. So this is also the big difference from the minimal hypersurface case. In minimal hypersurface case, Bernstein proved that n equals 2 case must be plane. And then later, n equals 3, 4, 5, 6, 7, the same result holds. But then n equals 8, there is a, no, n equals 7, there is a counterexample, which is not space hyperplane, but satisfy the minimal surface equation. Okay. So the minimal surface case situation changed, but the maximal surface case for any n, the graph maximal hypersurface defined on entire Rn is hyperplane. So this is also very different. One more.
If I'm correct, you were trying to say perhaps that for the minimal case, in Euclidean setting, this result is not true for Pn, arbitrary. Correct? Examples you are giving for the dimension 3, 7. Can you please repeat those examples?
Yes, okay. In R8, there is a minimal hypersurface defined on entire R7, and which is not the plane, hyperplane. Okay. So, but maximal surfaces, that case doesn't happen. Okay, thank you. So, other global properties is that also complete maximal hypersurfaces must be hyperplane. So this is for any n. Yeah, so complete maximal surface must be plane. Complete maximal hypersurface must be hyperplane. So we usually consider global property of surfaces. We assume the completeness or compactness, but there's no compact maximal surface like a minimal surface. So minimal surface case, we consider complete minimal surface, complete minimal hypersurface. But if we do the same things in maximal case, there is only one example, hyperplane. That's it. Also, there is no non-orientable space like hypersurfaces. It is, of course, obvious because if one chooses unit normal to do future pointing, then this is always future pointing. So the surface is always orientable. So, so we have these properties. So then maximal surfaces are not studied well, but in the recent 2 decades, some people are working maximal surfaces with singularities. Then we have we found interesting properties of global property of maximal surfaces. We have many complete minimal surfaces in Rn. Hypersurface, yes. Euclidean space, yes, yes. Counter example? Yes, there are many. A plane, you mean Bernstein theorem?
Complete maximal hypersurface must be hyperplaning?
Yeah, hyperplane, yes.
Yeah, but in the
Minimal.
Euclidean space, complete minimal hypersurface must be a plane or must be a hyperspace or must be a plane or there is some other example.
Yeah, many examples, minimal surface case, yeah. So then maybe second half of the 20th century, there are many global properties of complete minimal surface and minimal hypersurface is studied. So, and there are many interesting examples are found. So, but maximal surface case, this is it. So, but if we allow some singularities, then some define some completeness, then we find some interesting examples for as maximal surface case. Okay. Okay, now let's focus the n equal 2 case. Now I introduced the Weierstrass type representation. Okay, let U be a domain in R2 and F a maximal surface, and assume that xy the isothermal coordinate of F, and then very similar to the minimal surface case, we have this representation formula. Means if F is maximal surface, then there exists a meromorphic function G and holomorphic one form eta, so that F can be represented this way. Okay, and this integral is a path integral from fixed point z node to the variable z. Okay, so the proof is very similar to the minimal surface case, and yeah. So now we assume that xy to be the isothermal coordinate. Then the maximal surface case, each component of F harmonic functions, and the harmonic function can be described as a real part of holomorphic function. So by using this, we have this equality, and then the first fundamental form and second fundamental form can be described this. So the minimal surface case, this is plus again, but in this case we have minus here. And Weierstrass representation for minimal surface case, here minus and here is plus. So very small difference. Okay. And so first fundamental form can be described by using G and eta here. And the second fundamental form is 2 times real part of Q. And Q is defined by using eta and G. And Q is called Hopf differential. In the Professor Loftin's talk, it denoted by A, but in my talk, it's Q. Okay, and this G has a meaning, a geometric meaning. So let nu be the unit normal vector field on nu along F. And sigma, the stereographic projection from the hyperbolic plane to the disk. Okay, so the stereographic projection is like this is x1, x2, x3. So we have H2 plus here, and the unit disk here, and the correspondence is this point and this point. Okay. So so this G is a meromorphic function, but actually this is the composition of unit normal vector field and the stereographic projection. Okay, so thus we call G the Gauss map of the surface. Okay. So this is Weierstrass type representation. And so as I mentioned before, maximal surface is the global property of maximal surface as done by Calabi because its complete maximal surface is plane. But then later, some people allow some singularities of maximal surfaces, then found some examples. So as far as I know, Kobayashi, this is Kobayashi, Osamu Kobayashi. He investigated some property of maximal surfaces with cone-like singularities. And then in 1990s, Studio and Romero defined the generalized maximal surfaces. So, okay. So before, so since this is the first fundamental form, the modulus of G cannot be 1, right? Because then the first fundamental form degenerate. Or the isolated singularity occurs when at the zeros of eta. Okay. So Studio and Romero allows this to be 1 and this to be 0. So then define the generalized maximal surfaces. And then in 2000, two Lopez, Francisco Lopez and Rafael Lopez and so on, constructed Riemann type maximal surface. So there's a minimal surface found by Riemann. It's shapes like staircases, and they constructed a similar surface and investigate the problem. And then Arias, Chavez, Mira considered the building problem. And then Fernandez, Lopez, so on, consider some moduli space of maximal surface singularities. And also Imaizumi and Kato consider the flux problem of the surface. Flux is first given vector, then then construct the surface which corresponds to vectors. Okay. And then also Martin, Umehara, Yamada consider bounded maximal surfaces. Okay. Now, especially there is quite a big work by Umehara and Yamada, and they define the notion of max faces. So this is max, so definition is as follows. So F is a max face if there exists an open dense subset W of M so that the restriction of F to W is conformal maximal immersion. So this is really immersion. So singularity occurs point where M minus W, okay? And so they allowed some singularities, but they also define the derivative of F is non-zero. So the rank, so if the point is immersion, then the rank of DF is 2. So they allow the rank of DF is 1, at least 1. So, okay. So the singularity appears like a curve in a domain. Okay. So yeah. So Estudio and Romero, the definition of generalized maximal surfaces just followed here. So they don't assume this. So the point, the DF, the rank of DF is 0. They admit. But then isolated singularity occurs. And then so anything can happen. So, I mean, so for example, minimal surface case, the omitting value of complete minimal surface of Gauss map is at most 4. So, but if we allow this kind of singularity, df equal to 0, then so this theorem holds. In the maximal surface case, the same things holds. So we need this to investigate the surface to very interesting properties. So they define the max space this way. And so the isolated singularity is not allowed. So the first fundamental form of F might be degenerate. So first fundamental form is here minus. But if we change here plus, then this is immersion. This is already positive definite. And the set of singular points is exactly the P where the modulus of G equal to 1. Okay. So, and you see, so max phase, if we remove this, so then this takes value in C3. And then if we give a projection, real part of here and real part of here and the imaginary part of here, so we have a minimal surface. And in our setting of max phases, so if we use the composition of this projection, then we have minimal surface, really minimal immersion. Okay. So we have a duality between the max phase and the minimal surfaces. Okay, then Mihara Yamada defined the completeness of the surface to investigate the global property of maximal surfaces. Max phase F is complete if there exists compact set and symmetric 2 tensor T, so that T vanishes on M minus C. So T has compact support. And dA squared plus T is a complete Riemannian metric. Okay. So they define the completeness this way. And then they investigated some global properties of maximal max phases. Let F be a complete max phase, and G and eta the wireless data of F. Okay. Then there exists a compact Riemann surface M bar and finite points in M bar, such that M is biholomorphic to this compact Riemann surface removing with finite point removed. Okay. So the Riemann surface is always punctured Riemann surface. Okay. Punctured compact Riemann surface with finite points. So no disk is removed. Okay. And these data defined on M extend meromorphically to this M bar. So especially in particular, G can be considered as a meromorphic function on M bar. Okay. So G is defined on M bar compact surface into the, and this is meromorphic function, so this takes value at CP1, and this is holomorphic map. So we can consider the mapping degree, for example, mapping degree of G. Okay. And so the M is always represented this way. And this removed points corresponds to the end of the surface. So there is no compact max face, so like minimal surfaces in R3. Okay, then they showed that this inequality, let F be a complete max face and G eta the wireless theta. Then, so we can consider the mapping degree of G. So 2 times degree G is greater than or equal to the Euler characteristic of m bar plus 2n. And the equality holds each end, if and only if each end is properly embedded. Okay, so the point is, minimal surface case, we have this kind of inequality, and equality condition is the same. But the minimal surface case, they need finite total curvature. So they need to assume that the curvature is finite, total curvature is finite. But in this case, we don't need such assumptions. Because actually, they need negative part of total curvature is finite. But maximal surface case, the Gaussian curvature is always positive, I mean, non-negative. So the positive part, we don't care. So maximal surface case, we don't need such a finite total curvature condition. No. Compact, there is no compact max face.
We are taking complete max face, right? So there does not exist complete compact max.
No. So the number of this is always positive. Has to be positive. Okay. Okay. So also the singularities are investigated. So since we assumed some singularities, we have singularities, and then okay. So these three are very fundamental singularities. So these are not maximal surface. This is just a surface in R3, and I don't know the curvature. But okay, so this is define if we take this surface. So we have this line. This is called capital H. And we consider this surface, so we have singularity here, and this point is called swallowtail. So these are capital H. And also, we consider this surface, we have singularities here, and you see, this point is special point because the surface cross, okay, surface cross here. So capital H, but it crossed. So this is the special point called capital cross cap, and these points are capital H's. Okay. And in general, the two infinity map are called right-left equivalent. Then there exists local diffeo phi in a source space, and local diffeo in target space such that this holds. So, and we say that the singular point is capital H. If the surface, there exists, this is, the surface is right-left equivalent to standard capital H. So we said the surface has capital H. Okay, so these points are right-left equivalent to this this, yeah. Okay. So we have introduced these three singularities. And then we have criteria for singularities by using virus as data of the surface. Okay, let U be a max phase with virus as data. And we set alpha and beta this way. It's complicated, but just I want you to remember that alpha and beta are described by G and eta. Okay. So then P is singular point of F if and only if the modulus of G equal to 1. And F is right-left equivalent to a capital H at P if and only if real part of alpha and imaginary part of alpha are non-zero. Okay. So we understand we can, so if we compute these real part of and imaginary part and these are non-zero, then and it is G satisfies this, then we can say this is singularity is capital H. Okay. And F is right-left equivalent to swallowtail at P if and only if alpha is non-zero real number and the real part of beta is non-zero. And then also F is right-left equivalent to Caspar cross cap at P if and only if now alpha changed non-zero imaginary, okay, non-zero real to non-zero imaginary, and swallowtail case real part of beta is non-zero, but imaginary part of beta is non-zero. So these two singularity has some duality. And yeah, you see the maximal surface, we have this, this representation. So, and if we take imaginary part here, we also have a maximal surface. And this is called the dual, conjugate maximal surface of F. Okay, if we take imaginary part here. Okay, so then going back to the singularities, if the surface F has a swallowtail at P, then the conjugate surface has Caspar cross cap at P. And F has Caspar cross cap at P, then the conjugate surface has swallowtail. And the Caspar H is unchanged. So if F has Caspar H, then the conjugate has also Caspar H. Okay? And then we said something about generic singularity of max spaces. And let U be a simply connected domain, and H holomorphic function on U, endowed with a compact open CP topology. Then F max space with various theta. Then the theorem says that let K be an arbitrary compact set, and SK, we define SK, the holomorphic function on U, so that singular point of FH, F sub H are Caspar H, swallowtails, or Caspar cross cap, only these three. Then SK is open and dense subset of OU. So in this sense, we can say these three singularities are generic singularities of max spaces. And we have some examples. We set the virus theta as n power surface in as minimal surface, the same data. Then we have this kind of surface. So from top of view, we see that these are singular sets. Singular set. So in n power surface, G equal just Z, and eta equal dz. And so singularity is modulus of z equal to 1. And applying the criteria, we see that almost every point are Caspar edges here. But we have 4 swallowtails here and here and here and here. And between swallowtails, we have 4 cuspidal cross gaps here, 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 here. So then other singularities are cuspidal edges. But this is quite hard to find. Okay. And also, if we take the y-axis data, G equals Z, eta equal to G squared, what is Z? Then we have maximal catenoid. And in this case, singularity, so the singular set is again the circle, unit circle. But then the unit circle goes to 1 point. And so we have cone-like singular point here. And take conjugate surface, Z equals eta. So then we have helicoid, maximal helicoid. But then the cone-like singular point here changes to this singular point. So it doesn't look surface have singularities, but actually, so from this curve, the surface bend, so surface is fold. So the surface is 2-to-1 map. And this is called the fold singularity. Okay, so this 1 point corresponds to this fold singularity. Okay. Also, there are some other examples. Okay, let's see. This is from these y-axis data. We have 2 ends, 1 and -1, and using from this y-axis data, we see that the surface looks like 2 n-path surface connected to 1 point. So this point is cone-like singularity. And this, then each upper half we have again cuspidal edges and 4 swallowtails and 4 cuspidal cross gaps. And the bottom half again we have cuspidal edges and 4 swallowtails and 4 cuspidal cross gaps. Okay. And also, Kim and Yang found a complete max face of genus 1 with 2 ends. And this is defined, this is the algebraic elliptic curve. So this defines a torus and -2 points. And using the y-axis data G and eta, they found a suitable C so that the surface is single valued, I mean, well defined on M. And the surface has, so torus -2 points. But unfortunately, there's no handles. I mean, they do have handles, but we don't see any handles. Okay, so minimal surface. So here catenoid. So in the minimal surface case, one cannot give any handles like this. We want to give a tunnels, but then the period problems cannot be solved. So this is proved. But in this maximal surface case, so catenoid has, we can adding handle to catenoid. So topologically torus -2 points. But surface looks like not torus. But yeah, so the cone-like point changed. So this complicates shape. So again, we have cuspidal edge here, and here, and here we have swallowtails. And between the swallowtails, we have we have 4 Caspel cross caps. Okay. So the singular set like this. This is a projection of the Z-plane of the torus. Yes, so we have singular set here and here. So, okay, one circle corresponds to this, and the other corresponds to this. I don't know, so two circles, right? And so we have 2 swallowtails each. So then total 4 swallowtails and Caspel cross caps. And the other singularities are Caspel edges. And then one can generalize the genus for any positive number. So now define MK this way. So this is Riemann surface define this algebraic curve. And this is a compact Riemann surface of genus K. Okay, and then remove 2 points for any positive K. And then again, we define the wireless state as this way. So we can prove that for any positive number, there exists positive integer K, there exists C, positive real number, so that the surface is well defined on M. Okay, so this is the surface of K equals 2 case, K equals 3 case. So the Riemann surface defined by this algebraic curve is visualized this way. We have first take K plus 1 copies of Riemann sphere, and then make 2 slits here between z equals 0 and 1, between 0 and 1, and minus 1 to infinity, so 2 slits. Then glued together like this. So this point is z equals 1, here z equals 0, z equals minus 1, equal infinity, something like that. So in this case, we have Riemann surface of genus 2. Okay. So the remaining time I have maybe 30 minutes. So let me show how to prove this theorem. So how to find this C? Okay. So this is we don't use any new technique but this is kind of we can say traditional style to construct a surface with positive genus. Okay. Okay, now we start. Can you see to see? Maybe. Is it better? Okay. So M bar K is defined this algebraic curve K to Z times Z square minus 1 to K. Okay. So first we want to so since this is the Riemann surface of genus K, so and to solve the period problem in general, we have 2K plus 2 loops is a homology base of the so we need to check the 2K plus 2 one cycle integral one cycle. And also, and 3 components. So we have 6K plus 6 equation to solve. But we have, the surface has highly symmetric. So okay, now let's see. Okay, define mu j orientation reserving conformal diffeomorphisms. It's 1, 2, 3, 4. Like mu1 zw equal just z bar w bar. Mu2 zw equals z bar and e to the 2k lambda I w bar. Here lambda is k plus 1, pi over k plus 1. And also mu3 minus z bar mu4 zw 1 over z e to the I k lambda c squared w. Okay, and also k1 is composition of mu2 and mu1, and k2 kappa 2 composition of mu3 and mu1. Okay, and then kappa 1, kappa 2 are automorphisms on M bar. Okay, and we have lemma that pi 1 of mk bar is generated by kappa 1 j of 1 gamma. Yeah, I will define gamma later. And kappa 1 j kappa 2 gamma. So these brackets are homotopy class, and j 0 to k, and gamma so gamma is defined this way, this loop. Okay, so, and also we can take a base point, P naught, so that, so that Z is real and Z naught is real and one naught, and W naught is real. We take this base point and define gamma this way. And then, so we have k plus 1 copy, but then like here, kappa 1 of P naught here. And then if we, so gamma is this curve, this loop, and this gamma and kappa 2, composition of gamma and kappa 2 is like here and here. So we have a slit here. So so this is first first half of gamma. So okay, let me see. Kappa 2, composition of kappa 2 and gamma. Okay. So gamma is this, and kappa 2 gamma is this loop. Okay. And then okay, let's phi be a C3 valued one form. So then f is written by real part, integral of real part of this phi. And then also R theta is a 3 by 3 matrix, so that cosine theta minus sine theta, sine theta, cosine theta, 0, 0, 0, 0, 1. Okay. Then direct computation said that kappa 1 of phi, is a R not theta. R2 k lambda times phi. Okay. And pullback of phi by kappa 2 is equal to R of minus k lambda phi. So we have just pullback of phi by kappa 1 is just multiple this O3 valued matrix. This is also. So, so if we consider we said the homology base is generated by these curves. But, okay, for example, we consider the loop integral of kappa j and gamma of phi. And this is just gamma of kappa j star phi. This is in general holds. And then we have R of some theta. Theta is one of these. Yeah. Then equal to R theta times, so this is real valued. So this can be go outside of integral. Then so we have this. So if the period is closed for this curve, then period is closed for this curve as well. So thus we said that proposition f is well defined, I mean single valued, if and only if real part of this loop is 0, 0, 0. So we only need to consider one loop. Okay? So not 2k times 2k plus 2 loops. Okay? Now, so the equation is, now we have 3 equations. Okay? This equal to 0, this equal to 0, this equal to 0. But the third component, is real part gamma is third component just 2g eta. And what is g? G is CWZ. Am I right? ZW. not true. Then eta WZ, W. Okay. And eta is dz over W. So 2z eta is dz over z just, okay? So, no. So we have 2c here. So then now we consider c as a real number. So, and 2c, so this dz over d is just z of log z, okay? So this is real part, 2c and real part of 2 pi I equals 0. Okay, so the third component is 0. So the remaining part is these two equations. Okay. So we have only two equations to solve. The first component and second component. The first component is 1 plus g squared eta and equal 1/2 of and eta plus g squared eta plus eta bar plus g squared eta. Yeah. And the second one is 1 minus g eta equal to 1/2 minus I have I here, and then plus I bar minus eta bar. Okay. So so we have minus I here. We have plus I here, and we want both to be 0. So then we multiply I to the second equation. Then okay, let's consider minus I. Then okay, minus I to be 0. Then okay, here I minus and minus, yeah, maybe. So then for the two equations to be 0, we add left hand side and right hand side. Then we have eta plus d squared eta equals 0. Okay. So this is equivalent. So we have this. We want this equation, okay, for the gamma. And so now let's check at order of eta and g squared eta. Order is equal to 0 of eta this is just computation is k minus. So this is 0. So order means order of 0 or poles. So if this is positive, then this is order of 0, and this is negative, then this is pole, order of pole. Okay. And order of eta at z equal 1 is 0. Yeah, so this is regular point. Okay, and order equal d square eta equal to minus k minus 1. This is just computation. And d squared, this is 2k. Okay, so eta has 0 of order k plus 1 at z equals 0. And eta is regular point, non-zero, non-pole at z equal to 1. And d squared eta has pole of k plus order k plus 1 at z equal to 0. So, and d squared eta has zeros of order 2k. Okay. So again, remember the loop gamma is defined this way. So the gamma surrounded 0 and 1. Okay. And we want the loop collapse to real line segment. So, it is easy. So for eta, because eta has no poles at these lines, so just we can collapse gamma to this way. Okay, then we can evaluate. But it has problem, yeah. So because d squared eta has poles at d equal to 0, so he want to collapse, then the integral diverges. So we cannot evaluate. Okay. Anyway, so first we just collapse the gamma to this line segment, this and this, and then we can evaluate eta is I just write an answer 2i sine k lambda times 0, 1, 1 over k plus 1, 1 minus t乗 k over k plus 1 dt. Okay. And this is positive. And we said this is bk. Okay. Now, so we can compute this, okay, like this. And now, so the problem is this part. So because g squared eta has pole here, so but then there is a standard way to avoid this problem. Okay. So lemma. G squared eta plus c k plus 1 d equals minus 2, 1. So this equation holds. Okay, this is just a straight computation, straightforward computation. And this is nothing, but good things is we just add from g squared eta to exact one form. And then we get this. And this is holomorphic on the domain, it's surrounded by gamma. So, and also, yeah, okay, so then since this part is exact one form, okay, we can add this part, integral of this part, because this is exact form. And so we can add this. Okay, then g squared eta equal g squared eta plus this. Yeah? Then we have 2c squared So the integral of this is equal to this. And since this is holomorphic, except infinity, infinity, then we can collapse the loop gamma to the real line segment. Then one can compute I just write the answer is 4i c squared sine k lambda times 0,1 So this, we have this. And again, we set, this is positive. Okay. And so the period problem is solved. Period problem is solved if and only if C satisfies. So, okay, now we want this, yeah? So then we already have this, and we can compute this like this. So, and eta, okay, you can copy pk. Plus, then bar conjugate of this, in one conjugate of this. So then plus, no plus, minus 2ic squared sine k lambda ak equal to 0. Okay. So now we cancel 2i sine k. So then it is if and only if C satisfies bk minus 2 square ak equals 0. So C equals 2, not really. 2, I was wrong, 2 times 2. So, sorry. Here we have 2. C satisfies square root of 2ak. This is positive. So if we define C this way, then the surface is well defined on M. So in such a way, we can solve the period problem. And in minimal surface case, complete minimal surface of with two embedded ends must be a catenoid. So one cannot adding handle to the catenoid, but in this case, we can adding handle to the catenoid. Okay. So in this way, we can get these surfaces. Okay. And also, when k is even number, okay, say so k equals 2m. Okay, one can write the Riemann surface this way. In this case, it can be considered as a double cover of some Riemann surface. So in fact, we set m prime, m sub m prime is like defined this way. Then this is genus 2m, and this is genus m. And then we have this projection from this surface to this surface like this. Then we can say that this is double cover. And then we set this G1 and eta 1 this way. Then, so G is a composition of G1 to this projection pi, and eta is composition pullback of eta 1 by pi. So, and these are the various data of the max phase. So, in this case, our setting, this is the Riemann surface is genus 2, but actually this is a maximal surface of genus 1, double cover of maximal surface of genus 1. So in this case, we have no k is odd number, and this is just Riemann surface of genus 3. But then genus 4 case, we can consider the surface as a double cover of Riemann minimal surface, maximal surface of genus 2. So in this way, we have two families of genus Riemann surface, maximal surface of positive genus with two ends. Okay, so okay, and now I stop here, and tomorrow I will talk about non-orientable maximal surface. So we don't have non-orientable surface in L3, but if we allow singularities, then the direction of unit normal changed across the singular curve, then we can define the non-orientable surface. So tomorrow I will give the talk about this. So today I finish here. Thank you very much.
Okay, any question to the speaker?
Conjugate. Conjugate is. Yeah, the same. Just we multiply I.
About replacing real instead of replacing the real with imaginary.
Yes, the same.
Is that right?
Yes, that's it. Yes.
So is that equivalent to the definition we have for completeness?
Yes. But yeah, then the completeness is sometimes a problem. For example, maximal surface, maximal catenoid. So this is complete because the compact set is singular set is compact. But then we take conjugate, then the singular set is not compact anymore. So this is not complete. So the completeness is depends on if we take minimal surface case. If this is complete, then this is also complete. But the maximal surface case, complete is not invariant.
Also, you just wrote it on space like.
Space-like?
Why do you call it space?
Space-like is tangent space is space-like. So in any tangent vector has positive lengths. Any tangent vector to the surface has positive lengths. So inner product is positive. So the singularity is actually the tangent plane is right-like. So some non-zero vector has zero lengths, like right-like vector.
Further questions? Okay, if there are no more questions, let's thank the speaker again.
Thank you very much.